On a quiet day in the summer of 2023, something strange happened almost 12 billion miles away from Earth, and almost nobody noticed. A tiny machine, smaller than a car, had been talking to us every single day for 46 years straight. Then, without warning, it stopped. Not completely. A weak little signal was still trickling in like a heartbeat you can barely feel. But the real message, the flow of science and readings that had never once broken since the 1970s, simply went dead. At NASA's control room in California, engineers stared at their monitors and saw nothing where there should have been something. And then the truth hit them. This was not a problem they could just walk over and fix. To send a single command to this machine, they would need to wait 18 and a half hours just for it to arrive. Then another 18 and a half hours to learn if it had even worked. And on top of that, the very nature of the fault meant their message might never reach the spacecraft at all. This is the real story of what happened to Voyager 2 during those tense weeks of 2023. How the most distant working machine humans have ever built lost its voice, how a small team of engineers tried something with almost no guarantee of success, and what that spacecraft has been telling us ever since it came back online. Information that is rewriting what scientists thought they understood about the edge of our solar system and beyond. If you enjoy stories like this, stay with me because this one has layers most people never hear about. Let us rewind first, back to where it all began. Voyager 2 lifted off on August 20th, 1977, 16 days ahead of its sister craft, Voyager 1. Even though its number comes second, Voyager 2 was actually sent on the longer and more difficult route. While Voyager 1 was aimed at just 2 planets, Voyager 2 was given a rare opportunity, a chance to fly past Jupiter, Saturn, Uranus, and Neptune in one continuous journey, using each planet's gravity like a slingshot to reach the next. This kind of planetary lineup only happens once every 175 years. The scientists of that era understood they had exactly one shot, and they took it. Nobody expected this mission to last as long as it has. The plan was for around 5 years of real scientific work, and then a slow fade into silence somewhere past the outer planets. But Voyager 2 refused to follow the script. It kept flying, it kept sending data home, it kept running on machinery that today's engineers describe as almost impossibly tough for its age. By 2018, Voyager 2 had already been active for 41 years, and it achieved something only one other object in human history had ever done. It crossed the heliopause, the invisible wall where the sun's influence finally fades away and true interstellar space begins. We will circle back to what it discovered out there, because it is genuinely astonishing. But first, let's talk about the silence. To understand what really happened in July of 2023, you have to understand one unbreakable rule of physics that governs everything about talking to a spacecraft this far away. Radio waves travel at the speed of light. Nothing in the universe moves faster. Because Voyager 2 sits so incredibly far from us, even a message moving at light speed takes 18 and a half hours just to reach it. Then another 18 and a half hours for any reply to come back to Earth. Added up, and a single round trip of communication takes 37 hours minimum. You send a question. You wait more than a day and a half. Then maybe you get an answer. If that answer raises another question, you wait another 37 hours. Every test, every fix, every tiny adjustment moves at this crawling pace. There is no shortcut. Physics does not care how urgent your problem is. On July 21st, 2023, a team at Mission Control was sending a routine batch of scheduled commands to Voyager 2, the kind of ordinary maintenance task they had carried out countless times over the decades. But somewhere inside that routine sequence, a mistake slipped through. The wrong version of an instruction was sent up, and the damage it caused was very specific and very serious. Voyager 2's large dish antenna, the one piece of hardware responsible for both receiving instructions from Earth and beaming scientific data back home, tilted just 2 degrees away from where it needed to point. 2 degrees might sound like nothing. In almost any normal situation, an error that small would not even register as a problem. But across a distance of over 12 billion miles, 2 degrees is a massive gap. From where Voyager 2 sits, Earth is an impossibly tiny target in the sky. The antenna needs to aim with incredible precision to keep that connection alive. A shift of just 2 degrees was more than enough to sever it entirely. Suddenly, Voyager 2 could not hear anything sent from Earth. It could not send anything readable back, either. And the team on the ground, despite every tool and every ounce of experience they had, were nearly powerless. Because the very commands needed to correct the antenna could not reach a spacecraft whose antenna was no longer facing the right way. The engineers quickly weighed their choices, and there were not many. One option was to blast an extremely powerful signal from one of the biggest ground stations available and hope that even with the antenna slightly misaligned, enough of that signal would still land on the spacecraft's receiver. The mission's project manager, Suzanne Dodd, was honest about the odds. She said plainly that the chance of this working was low. Not zero, but low. The second option was simpler and far more certain, but it meant waiting. Voyager's onboard systems are programmed to automatically reset its orientation several times a year, purely as insurance against situations exactly like this one. The next scheduled reset was set for October 15th. That was the guaranteed fix. The problem was that October was months away, and losing months of data from a spacecraft sitting in a region of space that humanity might not have another working instrument in for decades was not something anyone wanted to accept without a fight. So through the final days of July, the team took a slower, more careful approach. Using several stations from the Deep Space Network at once, they simply listened. Not for actual data, just for the carrier signal, the basic radio hum that any powered spacecraft constantly puts out, sort of like a pulse confirming the machine is still alive. Finding it would not fix anything by itself, but it would tell them the spacecraft was still functioning and still on the path it was supposed to be following. On August 1st, 2023, they picked it up. Ground stations detected Voyager 2's carrier signal. It was weak, much weaker than usual because the antenna was aimed the wrong way, but it was undeniably there. The machine was alive. That single detection changed everything about the situation. It confirmed the spacecraft itself was fine and working exactly as it should. The only issue was the direction its antenna happened to be pointing, and it gave the team a new piece of hope. If a signal that faint could still be picked up on Earth, then maybe, just maybe, a strong enough transmission sent from Earth could reach the misaligned antenna too. On August 2nd, 2023, they decided to try. The ground station in Canberra, Australia, chosen because its position in the southern hemisphere gave it the best possible angle toward Voyager 2's current location, fired off what the team nicknamed an interstellar shout. It was a massive radio transmission, 100 kilowatts of power, blasted at full strength toward the last known position of a spacecraft whose receiving antenna was facing the wrong direction, across a gap of more than 12 billion miles. The message it carried was short and simple. Turn your antenna back toward Earth. The signal left the ground on August 2nd, and then there was nothing left to do but wait. 18 and a half hours for the message to physically travel to the spacecraft. If it was received and understood, another 18 and a half hours for any confirmation to travel back. In total, 37 hours of pure uncertainty. Now, layered onto this drama is a scientific detail worth understanding, because it explains why this rescue mattered so much beyond the immediate crisis. Years earlier, scientists had compared what Voyager 2 recorded when it crossed the heliopause with what its twin, Voyager 1, had recorded at a different location 6 years before. The two probes crossed this boundary at different points, heading in different directions, at different angles relative to the sun's equator. Voyager 1 crossed toward the north, Voyager 2 crossed toward the south. If the bubble surrounding our solar system were a perfect symmetrical sphere, both crossings should have looked more or less identical. They did not. Voyager 2 found a noticeably thinner boundary, stronger magnetic activity, and plasma conditions that were measurably different from what its twin had detected. This mismatch told researchers something important, that the bubble surrounding our sun, known as the heliosphere, is not a neat, even ball. It is shaped and squeezed by its constant collision with the material drifting through interstellar space, pushed inward in some directions and stretched outward in others. Together, the two Voyager crossings gave scientists their only two real data points describing this lopsided shape, a shape no theoretical model had accurately predicted before either spacecraft actually got there. This is exactly why the 2023 communication blackout and the desperate effort to fix it carried weight far beyond a simple technical fault. Because that aging spacecraft, running on decades-old parts and shrinking power reserves, remains the only tool humanity has ever operated south of the solar system's equatorial plane while inside interstellar space. If it had gone dark permanently in July of 2023, that unique scientific vantage point would have been lost for good. There is no backup mission funded to replace it. Nothing else is currently on a path toward that same region of space on any timeline that would help scientists working with this data today. The shout sent from that Australian dish and the agonizing 37-hour wait that followed was not only an engineering rescue mission. It was an effort to protect a scientific window that exists absolutely nowhere else on Earth. Since that rescue in August 2023, Voyager 2 has kept working. Its instruments have continued gathering readings on plasma, magnetic fields, and high-energy particles drifting through interstellar space. Its power supply keeps shrinking too, losing roughly 4 watts of energy every year, forcing engineers to shut down individual instruments one at a time just to keep the rest of the spacecraft alive a little longer. Not long ago, following the same path as its twin, another instrument had to be permanently switched off simply to preserve enough electricity for the ones that remain. Every one of these shutdowns is final. There is no turning something back on once the power needed to run it no longer exists. The people who work on Voyager 2 today have spent decades building something that feels less like managing hardware and more like maintaining a relationship with an old, distant friend. Many of them never touched the physical spacecraft with their own hands. Some were not even born when it left Earth. They test every single command on duplicate hardware kept in labs before ever sending it. Because there is zero room for error, and no possibility of physically checking anything once it fails, they still write instructions in programming languages that were already outdated before most of them started their careers. And whenever the spacecraft does something unexpected, they solve it the exact same way the team did during that stressful summer of 2023. Slowly, carefully, fully aware that one wrong move out there is permanent. What they are protecting is not just an old machine drifting through the dark. It is currently the only living, functioning instrument humanity has inside interstellar space, sending back real information from a region that no telescope, no computer model, and no theory built entirely from data gathered on Earth has ever managed to accurately describe ahead of time. The boundary that scientists expected to be a slow, gradual fade turned out to be an unexpectedly sharp line. The plasma out there that was predicted to be freezing cold turned out to be noticeably warmer than anyone anticipated. The magnetic field that scientists assumed would behave in a certain predictable way instead revealed a barrier structure nobody had built into their models. Nearly every prediction turned out to be wrong in some meaningful way. And the only reason we even know we were wrong is because there is a machine physically sitting inside the place we misunderstood, still transmitting, still measuring, still connected to a team of engineers who spent 37 anxious hours in August of 2023 hoping that a shout across 12 billion miles of emptiness had actually landed. It had landed. Voyager 2 came back online, and right now, at this very moment, it is still out there, still traveling at around 34,000 miles per hour, pushing further into the space between the stars, still radioing home information about an environment that every single model built before it arrived got wrong in some important way. At some point in the early 2030s, its power will finally drop below what is needed to run even one remaining instrument, and its signal will go quiet for the last time. After that, the spacecraft itself will not actually stop. It will keep drifting silently in a straight line forever, carrying with it a golden record, a companion piece to the identical one riding aboard Voyager 1, packed with greetings, music, and sounds of Earth chosen decades ago to represent our entire civilization to whoever or whatever might one day come across it. It will keep traveling long after every single person who ever worked on this mission is gone. But for now, right now, it is still talking. And what it continues to say about the space beyond our solar system is turning out to be very different from everything scientists believed before it ever got there. Let's take a moment to appreciate the incredible piece of infrastructure that made this whole rescue even possible in the first place, because it is one of the most remarkable engineering achievements most people have never heard of. It is called the Deep Space Network, a set of massive radio dish stations positioned at 3 carefully chosen spots around our planet. One sits near Goldstone in the California desert, another near Madrid in Spain, and the third near Canberra in Australia. These 3 locations were not picked randomly. They sit roughly 120 degrees apart around the globe, which means that no matter how the Earth rotates, at least one of these stations always has a direct, unobstructed line of sight toward any spacecraft drifting through deep space. Our planet never fully loses contact with its most distant machines. Each of these stations houses several dish antennas of varying sizes, with the largest stretching an incredible 70 meters across. These are some of the most sensitive radio receivers ever constructed. They are capable of detecting signals so faint they are almost nothing. Tiny whispers of electromagnetic energy that have crossed billions of miles of empty space to reach them. And they can aim that sensitivity precisely enough to track a fast-moving spacecraft with pinpoint accuracy. The Canberra station was the one chosen to send that desperate shout on August 2nd, and it was selected purely for geometry. Because Voyager 2 is heading south relative to our solar system's equatorial plane, the Australian station had the clearest, most direct angle toward the spacecraft's position. A 100-kilowatt burst of energy from a 70-meter dish aimed at the exact coordinates of a spacecraft sitting more than 12 billion miles away. That this is even physically achievable says as much about the nature of radio waves themselves as it does about human engineering. Unlike sound, radio waves do not fade the same way. They spread out, weakening according to the square of the distance traveled, meaning that by the time this powerful signal actually reached Voyager 2, it had become extraordinarily faint, but faint enough to still be picked up by an antenna, even when tilted 2 degrees off course, was exactly enough to work. And it did. Now think about what it must have felt like for the engineers sitting there, waiting. The shout went out at a precise moment on August 2nd. 18 and a half hours later, that signal would theoretically reach the spacecraft. If Voyager 2 actually received it, understood it, and executed the correction, its antenna would swing back around toward Earth. It would then need a bit of time to confirm its new position and begin transmitting again. Only then would that new signal begin its own 18 and a half hour journey back home. The earliest possible moment anyone could expect confirmation was roughly 37 hours after the shout was first sent. But even that number came with uncertainty, because nobody knew exactly how long the spacecraft might take to execute the reorientation once it received the command. So the team simply sat there inside a window of genuine uncertainty, knowing only that somewhere between 37 hours and some slightly larger unknown number, they would either hear something or they would hear nothing at all. At 12:29 in the morning on August 4th, 37 hours after that signal left Earth, Voyager 2 began transmitting science and telemetry data again. Its antenna was locked back onto Earth. The command had worked. The spacecraft was functioning normally and remained exactly on its expected path. 14 days of silence ended not gradually but all at once. The very moment that reoriented dish locked onto home and immediately began pouring out everything it had gathered while it was cut off. Those 14 days are worth sitting with for a moment, given what Voyager 2 actually represents. It remains the only scientific instrument humanity has ever operated south of our solar system's equatorial plane while inside interstellar space. There are only 2 real data points available from the crossing of the heliopause and the region beyond it, one gathered by Voyager 1 to the north and one gathered by Voyager 2 to the south. Every scrap of information Voyager 2 collects adds to a picture that simply cannot be built any other way. No telescope on the ground can substitute for a physical instrument actually sitting inside interstellar space. No computer model can replace real measurements taken there. And there is no second spacecraft currently on a path to reach that same region if Voyager 2 were to stop working. It is worth comparing this to a separate, even longer crisis that Voyager 1 went through just a few months later. In late 2023 and continuing into 2024, Voyager 1 suffered a failure in a memory chip inside its onboard data system, causing it to send back garbled, unreadable information for roughly 5 months straight. That situation was fundamentally different from Voyager 2's antenna problem. The antenna issue was purely a matter of physical orientation, something that could theoretically be corrected with a single, well-aimed signal. The memory chip failure, on the other hand, was internal hardware breaking down, something that forced engineers to completely redesign how the spacecraft's software was stored and run, all remotely, across a communication delay of over 22 hours each way, using programming methods from the 1970s. Both situations carried the exact same underlying pressure. Every wrong step could be the final step, because there is no repair crew out there and no way to physically inspect anything. Both crises eventually ended in success, and both left the scientific community with a sharp awareness that the time window for gathering data from these 2 aging spacecraft is limited, shrinking, and completely irreplaceable. There is something about this story that goes beyond ordinary engineering, something harder to put into words. Voyager 2 was designed and built by people who are now in their 70s, 80s, and 90s. Some of them are no longer alive. The spacecraft they created has now outlived its original planned mission by roughly 4 decades, and is currently being kept alive by a new generation of engineers who were not even born when it first launched. The deep understanding of how it works, its quirks, which commands are safe to send, and which ones are dangerous, now lives inside a small team at Mission Control, who spend their working lives communicating with 2 machines that most of the world has completely forgotten about. When something goes wrong out there, there is no instruction manual written specifically for that exact situation. There is only careful reasoning, creative problem solving, and full acceptance that the margin for error is essentially nothing. What that team saved back in August of 2023 is still running today. Voyager 2 is now farther from Earth than it has ever been in its entire history. Its power is weaker than it has ever been. Its working instruments are fewer than at any earlier point in its long journey. But the ones still active continue measuring, continue recording the details of an environment that no other instrument anywhere has access to, continue whispering home in a thin, faint signal powered by the fading heat of decaying plutonium. When it finally does go silent for good, that moment will not make headlines around the world. It will not lead the evening news. But within the small scientific community that studies the edge of our solar system and the vast interstellar space beyond it, the end of Voyager 2's transmission will close a window that took 46 years to open, and one that cannot realistically be reopened on any timeline in the near future. For now, though, that window is still open. The signal is still arriving. Back in the summer of 2023, a 2-degree error very nearly closed that window forever, until it was answered with a 100-kilowatt shout from a dish sitting in the Australian desert, 37 tense hours of waiting, and a spacecraft 12 billion miles away that, against real odds, decided to listen. And what Voyager 2 actually discovered the very moment it crossed out of our solar system back in November of 2018 is a story on its own, one so significant that 5 completely separate teams of scientists felt the need to publish 5 separate research papers about it on the exact same day, and not one of those papers matched what the textbooks had confidently predicted.